Hello and welcome to Weather 101. I'm Dave Brooks. This is a podcast that is all about trying to educate people on the world around them, and in this case, one piece at a time for weather. Now, since this is the first episode of Weather 101, a little bit of an introduction as to what you can expect through the podcast series. Now, one thing you're going to learn about weather in itself is that it's very difficult to explain in a very blanket statement how weather works. It's not like a car. Well, the engine turns and that makes the wheels turn and then you can go. Well, that's a pretty easy explanation, but weather, a whole lot more involved. In fact, once you realize that weather is one giant machine and each of the components of the machine are its own cog, it kind of helps to understand the cogs, to understand how it all goes. One big word to really explain how weather works is symbiotic, which is defined as an interdependent relationship. So when one thing changes, it has an influence on the rest of everything, and sometimes that's why forecasts are sometimes less than accurate. One little thing changes, and everything else gets put out of whack. So we'll take a look at how these individual components work, and when something changes, it gives you a better idea of how it all goes. The idea of this podcast is going to be that it is focused on the individual components, whether it's air pressure or wind or thunderstorms or severe weather, it's its own component, because that's really how to understand weather is how each component works and how it relates to other components. So when you can understand the small parts, you'll understand how they interrelate, how they are symbiotic, and then you finally start to understand how weather works. The other big goal of this is for everybody to understand the world around them. You don't need to be an expert. You don't need to be a meteorologist to understand what it is around you that's happening and why it is that it's happening. Looking at a beautiful sunshiny day with some puffy clouds is a gorgeous thing, but when you have a little more education, a little more knowledge, you can look at those clouds and realize that they're telling you a little bit of a story, and you can get an idea of what is or is not going to happen. Now, there's a few things to keep in mind as we go through this podcast, one of which is that rules are meant to be broken. Take, for example, everyone knows that at 32 degrees at sea level, water freezes. Then how come you can get freezing rain coming from the sky when it's below freezing in the high 20s? How does that happen? How do you get snow when it's above 32 at about 37 degrees, let alone ice pellets on the lawn when it's July and they're in the 70s or 80s? Why is it that those rules are broken? Because rules are meant to be broken. You're going to hear terms when you're talking about weather that involve the term tends to. When this happens, this tends to happen. It doesn't always happen, but more likely than not. So it's more rules versus tendency, with tendency winning out. Also, this podcast is being recorded for Paul Bunyan Broadcasting, which is based in Bemidji, Minnesota, north central Minnesota. So this podcast is really designed and tailored for life in northern Minnesota, which means there's many, many fantastical phenomena that are involved with weather that we're just not going to cover here. Hurricanes and typhoons, yeah, we don't tend to get those in Minnesota, so we're going to skip that chapter. Things like tides, they make a huge influence on the ocean, and technically, yes, the Great Lakes, they are affected somewhat, and since Lake Superior does border northeastern Minnesota, we could, but we won't. We're really going to focus on the kind of weather that's going to have a significant influence in life in northern Minnesota. So even though this is a podcast that's accessible online, and you can listen to this from any part in the world or country, we may skip over something that may be a little more pertinent along, say, the coasts. So keep that in mind. Now, first, before we get moving, my credentials. Like I said, my name is Dave Brooks, but I am not an expert. I'm not a meteorologist. I do not have a degree in atmospheric or earth sciences, but I am what you could consider an educated layman. I have had some official formal training in this, but again, I do not have a degree in anything that makes me an expert, but I do believe, like I said, is the mission of the podcast, to have a better understanding of the world around you. Now, my influence in this is that my primary job is working on the radio. Now, I've listened to many radio stations in many different states across everywhere, and I've heard people on the radio that when they're talking about weather clearly know what they're talking about. And then other people saying, well, we've got some yellow and red on the radar moving into the area. They clearly don't know what they're talking about. So in my job, it probably benefits me to know a little bit more about what I'm talking about so that I can deliver it to you in a more concise manner. So it benefits my job, but I'm also fascinated by weather because of how much of an influence it has on our daily lives. So I've made it a point of interest and for me to study on my off time and sometimes official time. Another influence for me on this was my dad. Now, my dad was a pilot for Northwest Airlines over 30 years. Now, if you don't think that flying in a vacuum-sealed metal tube where the weather lives at 30,000 feet up, if you don't think it benefits you to understand how weather works when that's where your job is in the sky, well, then you're not going to understand. But I think if you can understand weather, especially when it relates directly or indirectly to your job, it only makes you better at your job. So I am fairly well educated in the terms of weather, but again, not an expert. We turn to experts occasionally when we're going to need a little bit of science. Meteorologist Tom Szymanski, he's had a long career in meteorology, both TV and on radio. He's been doing it for over 30 years. He's an expert in the field. And we will turn to occasionally to get a little bit more of a scientific impression. And then when he's done dazzling us with big, complicated words, I'll kind of break things up a little bit and try to break it down for the layman. So the goal here is that you don't need to be an expert to understand weather, and that is really what we're gunning for. We want to make sure that whether you become better acquainted with weather or just have some question answered, I get it, that makes sense, then it's mission accomplished. So with the introductions out of the way, let's move forward with the first subject with Weather 101. Now, where do you start talking about weather? It's kind of like a metaphor, like painting a house. Where do you start painting a house when there's so much to do? Pick a corner, go from there, and eventually you'll get around to the whole house, and before you know it, the whole thing will be done. So one good place to start with weather, as good a place as any, is air pressure. Air pressure has a lot of influence on what makes weather work, probably as much, maybe if not more, than other big key components, so we figure we might as well bite off a big chunk right off the bat. So what is air pressure? You think about air pressure, you think about something that you have to have so much of in your tires on your car. But as relation to weather goes, what is it all about this air pressure? Well, like we promised, sometimes you need a little bit of scientific explanation, and for that, I give you meteorologist Tom Szymanski. So Tom, when we're talking about the barometers rising, pressures falling, mercury's on the rise, what are we talking about? What is air pressure related to weather?
Well, David, air pressure is a very important concept in terms of weather analysis and weather forecasting. We have high pressure systems and low pressure systems. And you'll notice if you listen to the weather, you'll hear a barometric pressure reading like 29.92 or 30.06 or whatever. I'm not even going to explain that because that'll confuse you more than you really need to be confused at this point. It's not really the number that's important. It's the trend. When you hear the barometer is falling or the barometer is rising, these are things to keep note of. When the barometer is falling, that usually means that lower pressure is on the way, and usually with lower pressure, you have increasing chances for precipitation or stormy weather. With high pressure moving in, the barometric pressure will be rising, and that usually means you could be expecting an extended period of fair weather. So nicer weather moves in when the barometer rises, usually, and as the barometer falls, a trend toward precipitation or stormy weather can be expected. These are not hard set rules. They are just general trends that can be expected when looking at weather maps and trying to forecast. When you're watching weather on TV, big blue H, that's high pressure, and the big red L, that's low pressure. And they do involve a lot of things as far as what type of weather to expect.
Okay, thank you. Now let's break down a little bit about what Tom Szymanski was talking about and try to make things a little easier for the layman. Now, how exactly a barometer works doesn't really matter for the sake of understanding how a forecast goes. Understand that what a thermometer is to the temperature, a barometer is for air pressure. But what exactly is the air pressure? Well, Tom kind of touched on it. Essentially, in layman's terms, it is literally the weight of the atmosphere above you. Air is made up of mass, and all things that are made up of mass have higher or lower density. So air included. Air can be of higher density or lower density, and that's what the pressure is. The higher the density of the air, the higher the air pressure. Now, some people out there that are listening to this podcast are kind of like me. They're visual learners. You kind of need to see it in order to really get it, and sometimes things that are of an abstract concept are difficult just to follow along. So here's a tip for those of you that are visual learners like myself. As you're listening to the podcast, go ahead and open a separate tab on your browser or on your handheld device or whatever you're listening to, and open up Google Image Search. Go in and type in high pressure, low pressure isobars and see what pops up on your Google Image Search, and this next description will probably help you out. I want you to use your imaginations or look at your Google Image Search, and I want you to picture a field, a nice big flat field. Let's, for the sake of argument, pretend that the pressure of the field is at sea level, so we'll call that 0. On one corner of this field, I want you to imagine a hill, not a steep downward cliff, Just a nice, gentle hill, something that would be good to sled down in the wintertime. In the other corner of this field, I want you to imagine a divot, a culvert, a ravine, some sort of a depression, a hole, however you'd like to imagine it. So you have this field with a hole on one side and a hill on the other side. Now, where the field is flat, we're going to say is 0. It's sea level. It's right at sea level. I want you to walk up the hill so that you're 10 feet above sea level. So 10 feet above where the ground is level. I want you to get one of those small orange flags that you'll see utility companies will flag in your yard when they're going to put in power lines, and I want you to put one in the hill there. I want you to take one step to your left or right, and I want you to place another flag while you stay 10 feet above the ground. Walk all the way around that hill, staying no more than 10 feet above sea level, planting a flag at every step. Eventually, you're going to make your way around to where you planted your first flag, and essentially what you've done is you've built a ring around the hill, okay? Now, I want you to go up the hill a little higher till you're 20 feet above sea level. I want you to do the same thing, place a ring of flags around the hill, marking 20 feet above sea level, so on and so forth till you get to the top. Then I want you to do the same thing with the hill. I want you to walk 10 feet below the surface of where the ground is, 10 feet below sea level, and I want you to mark some flags all the way around the hole. Now, essentially, as you continue to do this, you've basically got a lot of flags on this field, but you've also marked out the increments as to how high the field rises above or below sea level. When you do this to an actual hill, it's called a topographical map. It shows the rise and the fall. A topographical map would be a pretty good way to describe the air pressure systems, the highs and the lows and the in-betweens. Now take a look at it from the air looking down. What you've got is a series of rings circulating around the high pressure, which would be the top of the hill, and the low pressure, which would be this hole. And you've got a series of rings all the way around it. Now, they're not going to be completely circular. They may be oblong shapes, as a matter of fact, but they're really going to start to mark out what are called isobars. And if you're looking at your Google image search, you can see what we're talking about. Those isobars represent the grade, how steep the drop is from the high to the middle, or from the middle to the low. High pressure and low pressure, and you get an idea of where they're pressed together the hardest. So now you've got this field, the high part and the low part, the high pressure and the low pressure. Now imagine your car is a storm system. You put that car in the field, which way is it going to go? It's not going to roll up the hill. Instead, it's going to roll down into that depression. Well, the car represents the storm. Storms tend to be found in and around low pressure centers. So if you have a field that has this high pressure system, it's going to push the car away from it. High pressure systems are going to push the storms away from them. You're going to have the field with a low depression that's going to have the car roll toward it, or a low pressure center or a trough of low pressure having the storm systems develop in and around them. In a very basic layman's explanation of how high and low pressure affects storm systems, that's going to give you a bit of a visual example. Not exactly based on scientific principle, but it gives you a visual example of what we're talking about. So using this visual example, rather than us walking up the hill or walking down into the hole, it moves toward us. We stay still and it all moves around us. So as you're following the high and the low pressure with a barometer, when the barometer rises, it tells you that we're moving up the hill, so to speak. Fairer conditions, less clouds, less storm chances, more sunshine, more settled weather. Where if the barometer is falling, then it means we're either coming down the hill or we're moving our way into the hole, which means less settled weather, better chances for storms and cloud cover, and so on. Now, have you ever listened to the old timers and they'll say, well, I could feel it in my knees. There's a storm coming. They're not just whistling Dixie a lot of the time. Some people are more attuned to feel differences in air pressure. Now, Tom, you have a bit of an example as to how the old-timers can feel these things coming in, can't you?
One thing that people may have heard of or even noticed themselves, when you reach higher altitudes, when you're climbing a mountain or flying an airplane, your ears may pop. And that's because the air pressure is decreasing rapidly with height. That's because there's less air on top of where you are than when you're at the surface of the earth, when there's more atmosphere above you. Hence, decreasing air pressure, and that's going to allow for your ears to pop sometimes when you increase and or decrease in altitude when you're going in for a landing on an airplane, for example.
And much the way that a lot of us will feel it on our ears as we go up or down in the pressure on the airplane, some of us will feel it on our joints and our knees and hips and so forth. I know some folks, they know when it's going to rain because their hips get sore. As low pressure approaches, they can feel the effect pushing in on the fluid in their joints. They can detect that the low pressure is coming in, the high pressure is leaving, very much the same way that we can detect that we are rising or falling in the airplane based on what we feel pressure-wise on our inner ear. Now, Tom, something we touched on just very briefly was talking about the concept of building storms and how that is affected by high and low pressure. Why is it that storms tend to have a harder time building into higher pressure and an easier time building with lower pressure?
Well, David, precipitation, or any type of storm activity for that matter, depends on rising motion for its very existence. And by nature, high pressure is an area of denser air near the center with less dense air as you go further away from it, and denser air tends to sink. So near the core of high pressure, you have sinking air, and that's just counterproductive to producing cloud cover, which for that you need rising motion. And from that rising motion, if you get high enough in the atmosphere where the moisture condenses, you get the clouds forming, and enough moisture in the cloud obviously produces precipitation, and from that point forward they could develop into storms. Same process in the winter when we're talking about mixed precipitation and snow. Low pressure systems, where the air flows inward and counterclockwise around the center of the low, that involves rising air toward the center. So, as I've mentioned, when you need rising air for forming clouds and eventually precipitation, the more favorable environment for that to occur is around or near, or even better yet, near the center of low pressure versus high pressure.